Welcome back to my YouTube channel. In today's video lesson, I'll be discussing about a very important topic in chemistry, and it is simply called Bohr theory of hydrogen spectrum. Now, if you are just joining this community, my name is Bright Edo, a nursing science student from the prestigious University of Benin. And in the course of this video lesson, I'll be discussing about this topic. Now, this particular topic is very important for students who are in their first year, and also the science student to be precise, and also students preparing to write the post-UTME examination. Now, let's get into this video lesson. Now, the topic says Bohr theory of hydrogen spectrum. Now, it must be noted here that this scientist called Bohr is successfully accounted for the lines seen in hydrogen spectrum, because hydrogen as an element has various lines, has various spectral lines. So this man called Bohr in the year 1913, successfully accounted for the lines seen in hydrogen spectrum. So the next question we ask ourselves, what does the word hydrogen spectrum explain? Now, it must be noted here that hydrogen spectrum is a series of lines. This is something we must take note of for hydrogen spectrum. It is a series of lines that is seen. Okay, so inside hydrogen, we have various spectral lines, not just one. There are more than one. So hydrogen spectrum is a series of lines that is seen when light is emitted from a discharge tube filled with hydrogen, and it is viewed with a spectroscope. So this explains here that the instrument now that is used to view these spectral lines seen in hydrogen is simply called the spectroscope. Okay, it is called the spectroscope, like the instrument used to view small organism called microscope. Same applies for the instrument used to view these spectral lines in hydrogen, and it is simply called spectroscope. Now, the next question we ask ourselves, what are these spectral lines? What are these lines? Now, here are the lines. Okay, the spectral lines. The spectral lines. Now, these spectral lines has various values, which I will explain because it's going to help us when we start solving practice questions. So they are, the first one is called the Lyman. They call it the Lyman series. Okay, after the Lyman series, we have the Balmer series. Okay, the Lyman, the Balmer. Okay, after the Balmer series, we have the Paschen series. Okay, the Paschen series. After the Paschen series, we have the next, which is the next spectral line called the bracket series. Okay, after the bracket series, we have the other spectral lines or called the Pfund series. Okay, the P is silent, the Pfund series. And lastly, we have the Humphery series. So all of these are the spectral lines seen in hydrogen, to be precise. Every element in the periodic table have their own spectral lines. So for hydrogen, these are the spectral lines, and they are arranged serially. This must be noted, meaning that Lyman is number one. So we go like this. So Lyman is number one. Okay, the first spectral line, Balmer, Paschen, bracket, that's number 4. After that, we have Pfund, and lastly, we have the Humphery series. Remember, I said that these spectral lines have their own specific value. Okay, and they are the N1 value and also the N2 value. The reason I'm doing this way, because when we start solving practice question, that's calculation question, you're going to understand better how all this concept works. So I'm going to put a line here. to talk about these lines or these values for the spectral lines. So we go like this. It must be noted here that the N1 value is gotten from the arrangement to which the line is. Now, the first line is Lyman. What becomes the N1 value for Lyman? Always, it does not change. It is simply 1. This is something that must be noted. So, the way we get our N2 value is by moving towards the next number after your N1, in the sense that this is N1, we've gotten N1 for Lyman to be 1. So after 1, what's the next number? 2. So, and for the N2 value, we have 3 sets of numbers to write, because we're going to talk better on N2. So what do? So after we've gotten our N1 for Lyman to be 1, so the N2 for Lyman will start from the next number after 1. And what is that? It is 2. And I said we're going to write 3 sets of numbers. So 2, 3, and 4. This is how it works. I'm going to explain better as we progress. Now, what about brackets? How do we get our N1 value for brackets? It does not change. Remember I said it is gotten from the arrangement. So so for the Balmer series, okay, the Balmer series, okay, the N1 value becomes 2 because of the arrangement. And how do we get our N2 value? You move after 2, which is the N1 value for Balmer. What is the next number? 3. And we'll write 3 sets of numbers. So we'll go like this: 3, 4, and 5. I believe you are getting the concept. So here becomes 3, N1, you get it from the arrangement of the line, and N2 value becomes 4, because after 3 is 4, 5 and 6. So what about bracket? It is number 4, okay, 5, 6, and 7. What about Pfund? Number 5, 6, 7, and 8. And what about Humphery series? Okay, that's number 6, 7, 8, and 9. So all of these are the spectral lines for hydrogen and the N1 and N2 value, because this is going to help us greatly in practice questions. So you have to take note of this table, because I'll wipe it now, because I will write the formula here so I can explain how every single concept works. Okay guys, moving further, we have to take note of something very important, because when we start solving questions, we'll be seeing words like first line, and also we'll be seeing words like second line, and also we'll be seeing words like third line, as the case may be. Now, this is something that must be noted. For instance, we are to solve a practice question, and the question says calculate, because this concept has to do with wavelength energy and the Broglie's wavelength and the rest, which we're going to talk about as we progress. So they might say in a particular question, which we'll see very soon, calculate the wavelength for the first line in Lyman series. Okay, this is an example. Please pay attention. Calculate the wavelength for the first line seen in Lyman series. Now, we already know that for Lyman series, because anything I'm doing here, it applies to any other series. It applies to any other line. So you have to pay close attention to what I'll be explaining. So this is the Lyman series, and the question says calculate the wavelength of the what? First line. Now, this is something that must be noted. Remember, for Lyman series, what is N1 value? It does not change. It is 1. Because I said that when we start solving practice questions, you will see that all of these parameters will be in the formula, so we can start solving practice questions so easily. So we've got it. For instance, we are solving what becomes our N1, because you have to bring out your parameter before you apply the formula. So this is N1, and what is the N1 value? It is 1 for Lyman series. And the question, they were specific. They said calculate the wavelength of the first line. Very easy. How do I get the first line? For instance, if they said calculate the wavelength of the second line in Lyman series, how do I get the second line? And for instance, they said calculate the wavelength of the third line in Lyman series, how do I get the third line? Very easy. To do this, we use our N2 values. I believe you are getting the concept. We use what? Our N2 value. So the first line is the number we wrote first. The second line is the number we wrote after the first line. And the third line is the number we wrote after the second line. So this is the first line, second line, third line. Same applies. For anything I'm explaining here, same applies to this. So for instance, what's the first line of the Balmer series? 3. What's the second line? 4. What's the third line? 5. Same applies. So what's the first line of Lyman? It is 2. What is the second line of Lyman? It is 3. And what is the third line of Lyman? It is 4. So you can see how questions like this will be tackled without stress, okay? Because we have to understand the concept. So when we start solving practice questions, it's going to be very easy for us to understand. So let's get into the formula aspect of this video lesson before we start solving practice questions. Now, if you haven't yet subscribed to this channel, do well to click the subscribe button to this channel and also share these videos with your friends in other departments, okay? Make sure this video reach as much persons as possible. Okay guys, let's get into the formula part of this video lesson before we start solving practice questions. Because in this particular concept for the exam you are writing, because the questions they mostly ask is calculating wavelengths. We'll solve other aspects, but this one is very important. Though we ask you calculate wavelength, how do you do it? Very easy. And this is the equation. Okay, the formula is simply 1 over lambda, which is wavelength, is equal to this symbol, which I will explain as we progress, is equal to RH, which I'll tell you what it means. Open a bracket into 1 over n1 squared minus 1 over n2 squared. You close the bracket. So the question asks me now, what does these symbols represent in the formula? Very easy. Okay, it must be noted here that this one we are seeing as 1 over lambda is basically referred to as inverse of wavelength. Okay, inverse of what? Wavelength. Because in this questions to be asked, they will ask you calculate for wavelength. So after we've gotten inverse of wavelength, we'll solve for wavelength to be precise. They are all very easy when I start solving practice questions. So the next thing we'll do, now it must be noted here that this one that is seen as V bar, it is called wave number. It is same, okay? It is called what? Wave number. Both of these representations, they are the same, okay? It must be noted. Now, while for this one, which is RH, okay, RH is basically called Rydberg constant. Okay, this must be noted, and it has a particular value. And what is it? Rydberg constant RH, it is 109,678 cm raised to the power of -1, which is pronounced as per cm. And I'm going to talk more about the conversion as we progress in this video lesson. So you have to take note of this formula. I believe you can see N1, which when they give us a particular question, you know what to do. I believe you can see N2 and like that. So with all this said, now it must be noted here that this equation was described by a scientist called Johannes Balmer. Okay, Johannes Balmer, one of the spectral line of hydrogen. So this equation is called Johannes Balmer's equation. Okay, this must be noted. So I think with all this said, we are done explaining about the concept. So let's start solving practice questions. Okay guys, let's get into this first practice question. And the question says, calculate the wavelength of the first line in Balmer series. You have to understand the concept that they are asking us to calculate wavelength. This is something that will come to our mind. So solution. Okay, they are asking us to get wavelength. And now they mentioned a particular spectral line. Remember, we've talked about this spectral line. And which spectral line did they talk about? They mentioned the Balmer series. So when you see questions of this sort, what do you do? Very easy. So first of all, we have to understand the concept that Balmer series, for Balmer series, is it the first, second, third, fourth? Because there are about 6 spectral lines. So Balmer series, as explained, is the second spectral line. Do you get? Because the first one was Lyman, while the other is what? Balmer, like that, Paschen, bracket, Pfund, and Humphery. So we simply come here and say Balmer series is basically the second spectral line. So we know we have to get our N1 and N2 value. Very important, because we need this thing to solve the question. Okay, so Balmer series, what's the N1 value? I told you, you get it from this arrangement. Okay, it is simply number 2 when we count. Okay, what about N2? Remember, to get N2, start from the number you stop for your N1. And what was the value we had to work on? What's the value we had to work on? 3, 4, and 5. Remember all of these. Okay, now which of the line did they? Now, with all this said, what becomes our N1 value if we want to start solving? It becomes 2. And what becomes our N2 value? Which of the line did they mention? First, second, or third? First line. Remember your N2, you get your line. So what's the line for the first? This is our first line. Remember all of the explanation. First line, this is the second line, and this is the third line. So 3 is our first line. Okay, so with this, we cannot solve the question without stress. So what do we do next? First of all, we write our formula, and the formula is simply 1 over wavelength is equal to that wave number, which is same as 1 over wavelength, so we'll just leave it. Okay, equals to Rydberg constant equal to bracket, okay, 1 over what? N1 squared minus 1 over N2 squared. We'll then start imputing, because now we say 1 over lambda will now be equal to RH. Now remember, I said RH is a constant, which is 109,678, called Rydberg constant. Open a bracket, and it's expressed in what? Take note, it is expressed in per cm, as explained. Okay, we say 1 over, what's our N1 now? N1 is 2. Okay, so we simply write here as 2, and it is what? Squared. So minus 1 over N2. N2 is what? 3, and it's also squared. You close the bracket. So let's work towards what is inside the bracket first of all. So 1 over 2 squared, that's 1 over 4, or 0.25. Okay, so 0.25. So 1 over lambda will now be equal to 109,678 per cm. Okay, 1 over, sorry, I've evaluated this, and I had 0.25 minus. Now let me just be clear here. It must be noted here that most times they will say calculate the wavelength in nanometer. Take note, this is how the question might come. Most times it comes in this way, so you have to know, because now if you observe, the unit to which this value is expressed is in per cm, and they're now asking us to get our answer in nanometer, and we explain how that is done. Very easy. But before then, let us evaluate 1 over that's 1 over 3 squared. That's 0.111, like that. So 0.111. Okay, so what do we do next? We then evaluate it. When I say 109,678, open bracket, 0.25 minus 0.111, close the bracket, I had 1 over wavelength will now be equal to 15245.242. Okay, 0.242 per cm actually, because of the unit. Okay, so what do we do next? Because this is 1 over wavelength, so next we now say over 1. We will now then calculate for our wavelength. Okay, I believe you are following. So it becomes wavelength will now be equal to, I want to make it subject, so it's going to be like 1 times 1 all over the answer we had to get our wavelength. That's inverse. I believe you understand what inverse means. Okay, so 15245.242 cm per cm rather. Okay, I think cm is going to be cm because we've inverted. Okay, so the point here is this. So let's just solve. So it's going to be like 1 times 1 over 15245.242 5.242. That is lambda will now be equal to 6.56 times 10 raised to power of what now? 5. Okay, cm. But it must be noted here that question says put your answer in nanometer. So what do we do next? Take note, your answer, you will now times it by 10 raised to power of minus 2 times 10 raised to power of 9. Okay, this is how it's converted to nanometer. To convert your answer to nanometer, this is what you do. So we now then write our answer, which is the 6.56 times 10 raised to power what now? Minus 5 times this 10 raised to power minus 2 times 10 raised to power 9. So this becomes 6.56 times 10 raised to the power of minus 5 times 10 raised to the power of minus 2 times 10 raised to the power of 9. That is 656 nanometers. So this is the answer. This is how it is done. It is very easy without stress. Okay, because most times they will say calculate your and make sure your answer is in nanometer. So this is what you do. So your own question will be this. You solve for me, calculate wavelength of the third line, okay, of the third line in Balmer series, and I believe you know what to do. It is so much very easy. So with all this said, let's get into another way question can be asked. Okay guys, let's get into the next practice question, which is question number 2, and it says what is the wavelength in nm nanometers of a photon emitted during a transition from n equals 5 states to n equals 2 states in hydrogen atom. Now, if you observe this particular question, it's quite different from the one we solved earlier. They're actually the same way, okay? They're actually same type of question, but it's just that in this particular question, we're giving values. In the other, you just look for the value. They will say first, second line, or third line. But this one now, they made our work very easy. They gave us the value. And another question I would think you are thinking now is, which of those n1 or n2 value will I apply to the values given here? Now, this must be noted. It must be noted here that the lesser number goes to the n1, the higher number goes to the n2. That's what we do. So remember our formula, which says that solution, which says 1 over wavelength is equal to Rydberg constant equal to 1 over n1 squared minus 1 over n2 squared. It does not change. So 1 over wavelength equals 109,678 per cm. Okay, into 1 over what was an n1, the lesser number I said, minus 1 over 5 squared. So with these, our work is done. So let's solve. So it becomes 1 over 2 squared, that's 0.25. I think that's what we solve. That's what we solved for just now. Okay, so 1 over lambda equals to 109,678 per cm. Okay, into 1 over into 0.25 minus 1 over 5 squared. That is 0.04. So let's times with this. So 109,678 into 0.25 minus 0.04, close brackets, we are having 1 over wavelength goes to 23032.4, okay, per cm. So what do we do next? We will now look for our wavelength. To be specific, that's 1 times 1 over 23032.4 cm now, because the value is now down. Okay, so we have 1 over the answer 23032.4, that is wavelength will be equal to 4.342 times 10 to the power minus 5 cm. Remember what you do, make sure they are specific. Put your answer in nanometer. So we now say answer times 10 raised to the power minus 2 times 10 to the power now 9. So we are having 4.342 times 10 to the power minus 5 times 10 to the power minus 2 times 10 to the power 9. So wavelength will now be equal to 4.342 times 10 raised to the power minus 5 times 10 to the power minus 2 times 10 to the power 9. That is 434.2 nanometers. So that is how questions like this are being tackled without stress. It is so very easy. Okay, so I believe when you see questions like this in your exam, you can be able to solve them without stress. Now, if you are finding this video lesson helpful, make sure you share these videos with your friends because it's going to help you all. Okay, so with all this said, let's quickly go into another aspect on this video lesson. And now they are not specific, they are not asking us to get de Broglie's wavelengths. What do we do when we see questions of this sort? Because they are asking, because that's the question next one I'll be solving. Calculate de Broglie's wavelength. What do you do? That's what I'll be solving now. Now get ready. So make sure you're writing all of these in your notes. It's very, very important. Okay, guys, let's get into the de Broglie's wavelength concept. Now, when we see questions of this sort, what do? We have to understand something that before I solve this question, let me explain the concept of de Broglie's. Now, de Broglie's wavelength is still given with the symbol lambda, and we simply say lambda will now be equal to, okay, h over p, okay, whereby this h here simply means Planck's constant, and this symbol here is most common in physics, and it is given with is basically called momentum. Okay, and momentum is given by a formula which is mass times velocity. Okay, so we simply say the Broglie's wavelength will now be equal to h all over m times v, which is momentum, and it is mass times velocity. So, and in this particular question, they're asking us to get the Broglie's wavelength. Very easy. Without wasting much time, let's just apply. What's the Planck constant? It is a constant is given, which is 6.626 times 10 to the power minus 34 kilogram meter squared per seconds. Okay, times, okay, no times here, we'll just divide. What's the mass? Electron mass was given, and it is 9.11 times 10 to the power minus 31 kilograms times what's the velocity? Velocity was given to be 1 times 10 raised to the power of 6 meter per second. So 1 times 10 raised to the power of 6 meter per second. Now remember, de Broglie's wavelength, this wavelength, and it should be expressed in meters or nanometer or centimeter or as the case may be. But when we cancel our unit, we'll see the unit to which the answer will be. So I think kilogram can cancel kilogram, and this meter squared can cancel only this meter. So remaining just how many here? Just 1 meter. And seconds will cancel seconds. So I think with all these, let's solve. So 6.626 times 10 raised to the power now minus 34 divided by 9.11 times 10 to the power minus 31 times 1 times 10 raised to the power of positive 6. So we are having 7.3 times 10 raised to the power of minus 10 meters. Okay, because this is the only unit remaining. So you can see how questions under this aspect on the Broglie's wavelength is being solved without stress. Now we've come to the end of this video lesson. Now if you find this video lesson helpful, do well to click the subscribe button to this channel and also share these video lessons with your friends. Thanks for watching.